Okay, so before starting the next hour, just this, we have some didn't record the first several minutes of the lecture. So just make sure that everybody see again that we are going to have a midterm exam in February 10, Tuesday. And so this is going to be take-home exam. I'll give out the exam on February 10 and then collect on February 11. So as a result, we are not going to have class on February 10th. So you can use it class, a period to work on your exam problem. But again, this is the tentative, depending on how the government, funding progress. So hopefully everything goes okay. Otherwise, we have to make some change adjustment. Yeah.
So for the submissions, do you want hard copies handed into you, or do you want them like scanned and emailed to you in a PDF format?
Either one is fine.
Either one's fine.
Yeah.
So we just email it to you once we've done it.
Yes, if you are not on campus, you want to email me with the, those electronic copy. That's okay.
Okay.
Yeah, either one's fine.
All right.
All right, then let's go back to our formal lecture here. So what we are doing is now we talk about all the nice things, beautiful things, but now things are not always that beautiful. In other words, the element doesn't have to be nice rectangular shape or square shape. So we have, for example, little bit distortion, not much, from rectangular or square to very nice trapezoid, small, distortion of data. So how much this one is make, difference in the calculation of your element matrix. And again, the baseline is same. In other words, what we have derived in the previous slide, those derivation is exactly same regardless of the shape of the element in the physical coordinate system. In other words, which is going to be nice rectangular shape, or this shape, or even more, awkward, quadrilateral shape, doesn't matter. Derivation is exactly the same, except that now the coordinate of those nodal points are going to be different in the physical coordinate system. So in other words, the Jacobian matrix we developed, J11, J12, J21, J22, are exactly same, except that now this is going to be X1, X2, X3, X4, same thing, Y1, Y2, Y3, Y4. So those values are different, but the basic expression is exactly same, regardless what kind of element you are going to do in the physical coordinate system. So if you look at this one, node 1, again, we select 1, 2, 3, 4, counterclockwise direction, because the shape function is defined in the counterclockwise direction. If you want to say 1, 2, 3, 4, that's fine too, or 1, 2, 3, 4, that's okay, as long as it's going to be counterclockwise direction. If you say 1, 2, 3, 4, that's not correct because your shape function is not defined based on the sequence of the node. So here 1, 2, 3, 4, the first node that component -1 and +1 and +1 and -1. So in this case, everything is nice so that this eta and this eta cancel out, so that you got 1. So J11 is constant value 1. Very nice, because this is relatively, a nice shape. But if you look at J12, that's going to be y coordinate. So y1, -3/4, y2, -3/4, y3, 5/5, 5/4, okay. And then this negative x of 4 is going to be 1/4. So plugging here. So y has changed from nice shape to here because of this distorted shape. So because of that, now J12 is non-constant, also not 0. That's going to be 1 plus eta/4, function of c or eta. In this case, they are function of eta. So J12 is like that. Then likewise, J21, okay? Then again, this is gonna be X1, X2, X3, X4, then J21 happen to be 0, right? But J22, again, Y1, Y2, Y3, Y4, this is gonna be not constant, not 0, but function of C, 3 plus eta over 4. So what does it mean here? In this case, in terms of X coordinate, it's regular, both of them in the same X coordinate system, two nodal points, same X, same X. But Y has some, distortion. That's why you happen to have this kind of the matrix. So about the X coordinate system, 1, 0. But anything associated with the Y coordinate system, function of C and eta. So in other words, your Jacobian matrix is going to be like this one. Okay, that's the Jacobian matrix. Then you have to calculate the inverse of the Jacobian matrix. How do you do the inverse of the Jacobian? And 2 by 2 matrix, how do you do that? Some simple formula is that if you have A, B, C, D, 2 by 2 matrix, take the inverse, then that's going to be 1 of AD minus BC. That's going to be determinant of the Jacobian. And that's going to be D and A. So we exchange the diagonal term. And this become negative D and negative C. Put the minus sign. So that's the simple formula for 2 by 2. Of course, you can do it different way. That's fine too. But 2 by 2, you can do this one. Then if you invert this one, which is going to be like that. And the determinant of Jacobian is, which is going to be this term, is going to be this product minus this product. So this is going to be 3 plus C plus 4, and this is 0. So minus 0, so 0. So you got that one. So this one also show that the Jacobian, determinant Jacobian is going to be not constant. In other words, mapping from here, from nice C and eta coordinate system, this element negative 1 to 1, negative 1 to 1. So if you have this one, the mapping of this, the C and eta, and mapping of this one, dx over dy, this is not uniform. In other words, the mapping from there to here and mapping from here to here are not the same throughout the whole domain. So it's going to be function of C, okay, depending on the location, your mapping is going to be different. That's what it means mathematically. Then one thing, important thing is the mapping physically, this area, to have a physical, correctness, then area have to be some area here. So dc d eta have to be dx dy, and then area is going to be positive. You don't have negative area. So dc d eta, then dx dy have to be positive. In other words, the determinant Jacobian have to be positive. If this is going to be negative, that means something is wrong, because area become negative area that doesn't have physical meaning. So if you look at that, then our domain C is going to be negative 1 to 1, because that's the domain in the natural coordinate system of the C, negative 1 to 1. So between negative 1 to 1, this is always positive. So we have proper mapping. Even it's not uniform mapping, but mathematically that is proper. So anyhow, in that case, if you're going to calculate the derivative of the shape function, derivative of the shape function h1 respect to x, then r11 is going to be 1, and r12 which is going to be this, the fractional function, and of course this is going to be simple polynomial from H1, H2. So if you do that, that's gonna be the first derivative dH1 dc. Again, you can see that that's gonna be the fractional function, not the simple polynomial, right? And if you carry out same thing, dH1 of dy, then R21 and R22, R21 happen to be 0, this happen to be 0, but this is going to be also a function of C. So if you carry out this derivative and then multiply by this, that's going to be, again, fractional function. So what does it mean? If you evaluate this same thing, you know, Laplace operation, as we've seen in this derivative, dH1 over x squared and dH1 over y squared, then this square plus this square, and determinant of Jacobian is going to be this one, and then integration down to 1 to 1, then see that whether can you carry out this integration by hand analytically. Can you do it? So, for example, this is going to be negative 1 to 1, negative 1 to 1, and what is this term? Is this one. So negative 1 minus over 4 plus 1 plus eta and 1 minus c and 4, 3 plus c, and this whole thing square plus minus 1 minus c and 3 plus c, all things square, and then 3 plus c over 4 and dc and d eta. So if you look at that, do you think we can carry out this one analytically? Yes or no? You don't know until you try. You know, in terms of integration, if you have a fractional function, in other words, you have a function of denominator, right? Then 99% you cannot carry out analytical integration. Some special functions through some transformation of variable, sine, cosine, or etc., you know, we can do that. In general, any fractional function, analytical integration is going to be almost impossible. Okay, so we cannot carry out analytical integration. So that's why we are going to do numerical integration. Numerical integration, we can do that. So here is the fact. If you look at, if you taken, you know, the calculus, you learn how to differentiate and you learn how to integrate, right? Then in terms of analytical sense, in other words, if you want to do by hand, you know, pencil and paper, if you are given function, taking a derivative, taking integration, which one is easier? Taking derivative. Taking derivative, virtually any function, you can carry out the derivative. Even fractional function, type of, you know, whatever function, you can carry out derivative. But integral, if function become a little more complex, like a fractional function or some complex, you know, sine square times x square or whatever, then integration is not easy, almost impossible. So you analytically, derivative is much easier than integration. And numerically, you can carry out both, you know, derivative, like a finite difference technique is derivative, and integration, you can do both of them. But in terms of accuracy, because numerical, you can anyhow carry out those, you know, integration, differentiation itself. But in terms of accuracy, if you look at the accuracy of derivative, accuracy of integration, which one is going to be more accurate? Integration is going to be more accurate. So in other words, if you look at a function, If you look at the function like that. So finding slope in here, that's gonna be maybe exact slope, right? Then if I use the difference technique, then for example, this is gonna be the slope. You can see that this slope and this slope not close, right? That is quite different. However, if you look at, let's use different section. This is exact integration area under the curve, right? But numerical integration, even you use simple trapezoidal rule, so this make it straight. So you know that curve section integrate that one. The difference is very small in general. Okay, so numerical integration is much more accurate than numerical differentiation. If you same order of technique, if you use higher order technique, the difference may be different. But if you use same order of integration and differentiation technique, numerical integration is much more accurate than numerical differentiation. So as you carry out numerical integration, luckily, we are not going to lose much accuracy of this integration value. Okay, very accurately. So in other words, we can carry out this calculation, element matrix, very accurately using numerical integration. Any question so far? So then let's go to a little more extreme case just for illustration. Like this. So this is 0, 0. So we have a boomerang shape. The ninja used, this kind of the weapon, right? So this kind of the shapes. This is still 1, 2, 3, 4, four-sided geometry. And of course, your natural coordinate system is always referenced from -1 to 1, like 1, 2, 3, 4. Okay, this mapped into here. Then, if you trust me, in other words, that we are exactly doing same thing as this one, except that now x1, x2, x3, x4 is going to be, x1 is going to be 0, x1 is going to be 1, x3 is going to be 0, x2 is going to be -1. So plugging in here, then you come up with this Jacobian matrix. So again, as you expect, Jacobian matrix is much more complex than even the previous one. Like the previous one, Jacobian matrix was this one, right? So you got 1, 0, at least you got 0, but you don't have 0 anymore. Even this looks like symmetric. Non-zero value, again, function of C and eta. C and eta in here. All right. Then it looks fine. I don't see any problem. But now when I calculate the determinant of Jacobian, which is going to be this product minus that product, this minus that, you got this one. Right? You can easily prove that this multiplication minus that multiplication is going to be that. Then, okay, looks fine to me. Anything wrong with this one? Did you find something wrong with that one? What's wrong with this one? What I said in here, this determinant Jacobian have to be always constant for any point in the natural coordinate system. So in other words, if I pick any point in the natural coordinate system, this determinant Jacobian have to be always positive, right? Otherwise, physically something is wrong because area, positive area, map into negative area. Then look at here. Is there any possibility that it become negative? Yeah, for example, 3 is going to be 1, eta equals 0, then 2 minus 3, negative 1. Right? And also, c equals 0, eta is going to be, positive 1 or close to 1, then that's going to be 2 minus 3 is negative. So we cannot maintain this going to be all positive within this domain. That's not possible, right? That means this kind of element is not acceptable because it does not have proper mapping of the geometry. Mathematically, nothing wrong in here, but in the physical sense, the area map into negative area, that's not acceptable in the physical nature of the problem. So in other words, if you have an element like that one, that's not acceptable element. So what does it mean? If I do mesh, and let's say, Valentine's Day is coming in January, so let's say we have a heart shape. I have a domain like that. I'm going to have some finite element mesh. So someone said, okay, I'm going to do, mesh like this. One element, and the next element like that, and next element like that. So that's what I'm going to do, for example. Okay. Then this element is not acceptable. In other words, you are not going to get the right answer. Okay. Some programs stop immediately once they find it out. And other program, they may do the calculation because still, computer program can do the number crunching, but the answer is going to be totally wrong. Right? Then how do I make sure that this doesn't happen? This kind of situation doesn't happen. So whenever you look at the element, mesh in here, of course, this is the best element shape, like a square, the best shape. But now, in real nature, you cannot have this shape every, inside the domain because shape is going to be complex. So like this one, let me redraw this heart one more time. If you have this one, then instead of using element like that one, I have the element like this. Something like that, right? So the bottom line is that when you have a four-noded element, so extreme case is going to be like this. Right? So if you look at the internal angle of each nodal point, internal angle, this 90, 90, 90, 90, very nice. Of course, in that case, less than 90, little larger than 90, etc. But this case, whatever, let's say this 90 and less than 90, 90, but this is going to be what? What is this angle? Straight line means 180 degree, right? So the extreme case is going to be that is going to be 180 degree, that's it. If larger than 180 degree, like this one, this is larger than 180 degree, then you got problem with the Jacobian matrix. And obviously, we do not want to even have 180 degrees there because that, the round of error, even you say 180 degree, but it could be 180.001 or something like that. So ideally less than 180 degree. All right. And then mathematically that is acceptable. However, if possible, avoid this kind of shape of element. So make sure the element is going to be as close as possible to 90 degree of all internal angle. Of course, doesn't have to be exactly 90 degree, but as close as to 90 degree. If you do that in the mesh, then what it means that your numerical integration is going to be a little more accurate. So accurate solution is going to be obtained with that mesh. You see the point? Of course, some distortion of element is inevitable because of the nature of the geometry, but make sure that each element doesn't have too much extreme distortion so that you can maintain the quality or accuracy of the solution. Any question up to this point? Yes.
For some of the CFD only has the option to either have the square element or the triangle elements.
Yes, we are going to talk about that too. Triangle element. Yeah. And this isopatric element is also applicable to triangle element too, but more common for this quadrilateral element. Okay. So let's talk about now again higher order element. So we talk about four-noded quadrilateral element, right? But now we want to have more nodes. So in other words, we can represent the solution not linearly, but quadratically along the line. So I put 4 extra nodes. So this is 8-noded element. And this is 9-noded element. Right? Then what is the difference? What is pros and cons? So before we talk about pros and cons, one thing I can tell you here that we talk about today that here, this quadratic element in 1D. So if you do this quadratic element in 2D, I mean y direction, so like that. So this is c direction and this is eta direction in the natural coordinate system. So 3 shape function, then product is going to give you 9 shape function of this one. So in other words, this shape function can be determined from the product of this one and that one nicely. Okay, that's the beauty of this one. And this one, unfortunately, you cannot derive like that. You cannot derive from the product along the shape function in the c direction and shape function in the eta direction. You cannot do that. You have to derive this one in the conventional manner, assuming polynomial, and then do the standard procedure. So much more complex than this one in the derivation, but luckily people have already derived this one, so we don't have to develop this one from the scratch. So shape function are already provided in the textbook. Then what is pro and cons of this? That first of all, if you look at the boundary of the element, boundary has 3 nodes always, right? 3 nodes along the boundary. So the solution along the boundary is represented by quadratic polynomial. Same thing in here, quadratic. So I think I talked about this problem some time ago because somebody has a question that if I have, let's say 9-noded element here, right? And then this is mapped with 4-noded element. So this is each element, this one element, right? Then along this boundary, I said there are mismatch because solution in here, in terms of this one, is going to be quadratic, something like this. Okay. And in terms of this bilinear element, your solution is going to be piecewise linear, like this. So in other words, there is a discontinuity of solution of this much at the boundary between this element and that element. So in other words, this is going to cause error. So this is not acceptable mesh. Okay. Anyhow, then going back to here, going back to this one, the difference is just one node. There's internal node, and there's no internal node, and there is internal node. One node difference. Okay, along the boundary, all quadratic, but there's no internal node, there is a one internal node. Then what is the big difference between the two? Well, just looking at this one, it doesn't make big difference. One node less, or more. So in other words, bottom line is this one. If you construct the the matrix, element matrix for example, Laplace equation, this is going to give you 8 by 8 matrix, because you got the 8 node in the element, and each node has a single degree of freedom. This one will give you 9 by 9 matrix. So 8 by 8, 9 by 9, not big deal, right? But let's say if I have a problem, okay, if I have a problem and I have mesh, very defined mesh. So let's say 100,000 elements. Okay, 100,000 elements. Then this one and that one, if you same kind of element except that internal node, you are going to have 100,000 degree of freedom is going to be less using this element compared to this one, right? Because one element has 1 degree of freedom less, so 100,000 element means 100,000 degree of freedom less, right? That's the big deal. The size of matrix. In other words, system matrix is going to be much less this one for that one. I told you that if you increase the size of matrix by 2, then standard Gauss elimination technique, the computational time is going to be to the cubic power. So not linear, but computational time is going to be 8 times more intensive. So if you cut down this much, that is going to cut down quite a computational time. Okay, then what about the accuracy? I mean, this doesn't have the node in the middle. This has node in the middle. Then we are losing some accuracy in here because we don't have representation of node in here compared to this one, right? Then obviously that is true. This has more degree of freedom, so this is going to be more accurate than that one. However, lucky thing is this node, internal node, is not shared with any neighboring element, just confined within itself, right? So the impact of the node, internal node, is much less than the boundary node, because boundary nodes are shared by neighboring element. So overall solution is going to be affected by those nodes when you solve the problem, because solution have to be continuous throughout one element to the rest of element. So in other words, the impact of this internal node is much less than the impact of the boundary node. So in other words, this is more accurate than that one, but the impact of this internal node is not that much significant. So in other words, considering that, we want to cut down the excuse me, computational time, then people sometimes prefer this element over that. Okay, So that's the choice. Again, the choice by the user, which element they want to use for in terms of accuracy or in terms of excuse me, efficiency of the solution. Okay. Any question up to this point? Okay, then let's talk about triangular shape of element, right? In isoperimetric element. So triangular shape, we define shape function such way. One at the origin, and two is going to be c equal 1, and 3 is going to be eta equal 1. So we use define shape function based on this nice right equilateral triangle. Then the shape function is going to be written this way. So in other words, again here, when this is 0, 1, here 0, here 0, same thing. And this one 0, 1, 0. This is going to be 0, 0, 1. Okay, so same property we talk about in chapter 5. And high of the triangular element has 6 nodes. 6 nodes. And the shape function is given in here. Okay. Again, defined from 0, 1, 1 in terms of C and eta coordinate system, and the rest of it is going to be in the middle. Okay. And now, one thing also you have to excuse me, pay attention to this element. The load element is just the sequence where it starts from, like 1, 2, 3, then clockwise, counterclockwise. The higher the element, this one as well as this one. Okay, there are many choices. So, for example, this one, where you want to start from one of the corner. Then, this case, again, you are going to follow the clockwise. Okay, I mean counterclockwise. Sorry. Then I'm going to follow that. Then again, the choice is right now. The way we put is that 1, 2, 3, 4, the first corner node, and then mid node 5, 6, 7, 8. Same thing in here. The 9 is going to be the last one in the middle. Or someone want to say that I'm going to say 1, 2, 3, 4, 5, 6, 7, 8. That's fine. Whatever you want to, define the sequence of node, that's fine. But the main thing is going to be depending on how you number the node in here, your shape function is going to be associated with that particular node numbering. So in other words, if I use shape function in the book for this one, then whenever you have a finite element mesh in the domain, so in other words, let's say this is my domain, and one of element is going to be like that one. Then I'm going to use 8 noded element. Then if I'm going to use this shape function as defined this one, then you have to use one, call that connectivity 2, 3, 4, 5, 6, 7, 8. You have to read in the nodal connectivity exactly the same sequence as defined in here, Okay. Then the question is, if you want to use any commercial program like ANSYS or Abacus or whatever program we have, then how do I know that what kind of order of nodal sequence the program use? Then you need to check the element library. In the user manual, there is an element library. Element library show you this kind of element. All right, 4 noded, 8 node, 9 node, whatever they use in the program, they have that on, and they gave you this kind of nodal the value, either this way or 1, 2, 3, 4, 5, 6, 7, 8, whatever shown there. That means the program is based on that sequence of node for their shape function. Then you have to follow the same, sequence in your input of the data. Make sense? So it's the same thing in here too. Triangle element. One, in this case, we use again counterclockwise direction. 1, 2, 3, and then we pick the middle one, 4, 5, 6. Again, this is one way of doing that. And if you want to do 1, 2, 3, 4, 5, 6, you can do that too. But the shape function are going to be different depending on how you select the nodal point. Make sense? Okay, I think it's about time to quit. So let's stop here, and then we are going to continue from here next this Thursday.